So it's a pleasure for me to introduce Francesc Fité from MIT, and he will present about ordinary primes for some abelian varieties with extra endomorphisms. Thank you.
Okay, thank you very much for the introduction, and thank you very much to Victoria and Sawin for giving me the opportunity to speak here. I want to do three things in this talk. First of all, I want to present the conjecture on the density of a set of primes which are ordinary for an abelian variety defined over a number field. Then I want to discuss the beautiful results that we already know about this conjecture. And so this conjecture in particular is known when the dimension is at most 2. And finally, I will present some new results that I could obtain in dimensions essentially 3 and 4 when the abelian variety is special, when the abelian variety has some extra endomorphisms. So this third part of the talk will be based on a preprint that is now an archive, and you can see the link is here. And well, I want to apologize to the experts because I decided to keep this talk very basic and very friendly to graduate students and young researchers. So you will, I will give many definitions that for sure many of you know. So let me start by fixing some notations. Throughout the talk, A will be an abelian variety defined over some number field K of dimension G. And then for a rational prime L, I will denote by TL of A, the elliptic Tate module attached to A, which is defined as an inverse limit over N of the Q bar points of the L to the N torsion of A, and which is isomorphic to the 2G power of the elliptic integers. But most of the time, I will be using the rational elliptic Tate module, which you obtain by tensoring the elliptic Tate module with QL. And now let me attach to every prime of good reduction of A three notions. So let P be a prime of K of good reduction for A. Say prime of K, I will mean a non-zero prime ideal of the ring of integers of K. And then I will denote by A sub P the reduction of the abelian variety modulo P. And I will denote by P sub P the characteristic polynomial of Frobenius acting on the rational elliptic Tate module on VL. And well, because P has good reduction, this is well defined. And this is a polynomial which has degree 2G, and it has integral coefficients which do not depend on the choice of L we made, as long as we take P and L coprime. And finally, the last notation I want you to remember is this quantity UP. UP will denote the number of roots of the characteristic polynomial of Frobenius in an algebraic closure of ZP, which are p-adic units. And well, yeah, first observation is that this natural number is at most the dimension of the abelian variety. Why is this so? Well, because of Bayes' theorem, we know that the roots of the characteristic polynomial of Frobenius come in conjugate pairs, which multiply up to the norm of P. Therefore, at most one root in such a pair can have a p-adic valuation as 0. And now I want to define what it means for a prime P to be ordinary. And for this, I need to speak about the Newton polygon attached to the polynomial P sub P. Let me start from the very beginning and attach a Newton polygon to a general polynomial with coefficients in QP. So yeah, let V denote an extension to QP bar of the p-adic valuation. And then the way you build the Newton polygon is the following. You consider the set of points on the real plane, whose x coordinate is some index I that goes from 0 to the degree of the polynomial, and whose y coordinate is the valuation of the ith coefficient of the polynomial. And as an example here, I drew the Newton polygon of some polynomial of degree 5, for which I chose random valuations for its coefficients, and you plot the points, you draw the lower convex hull, and that's what the Newton polygon is. And yeah, the key property that you need to keep in mind in this talk about the Newton polygon is that it has this, so it's the following one, and it is that the x length of a segment of the Newton polygon, which has a rational slope s, is the number of roots of the polynomial which have a valuation s. So for example, on the example, if I look at this segment of slope 2, it has x length 1, and this is telling me that there's exactly one root which has a valuation 2. And yeah, this brings us to the Newton polygons that we can attach to the characteristic polynomials of Frobenius for abelian varieties. And well, in this case, these polynomials are special, so the Newton polygons have some further properties. So yeah, we know that. So yeah, P sub P is a characteristic polynomial, and therefore it is monic. So this already tells us that the Newton polygon starts at the point 0, 0. Moreover, Bayes' theorem tells us that the constant term of this polynomial is the norm of P raised to the dimension, and therefore, as far as we normalize the valuation so that the valuation of the norm is 1, this tells us that the Newton polygon will end at the point 2g, g. And since the Newton polygon is the lower convex hull of some set of points, this is already telling us that the Newton polygon will lie below the blue segment that you see on the picture that connects the point 0, 0 with the point 2g, g. But we also know that the coefficients of P sub P are integral. Therefore, all the points that we use to build the Newton polygon will lie above the x-axis. And we also know that the Newton polygon is almost palindromic. Sorry, that the characteristic polynomial of Frobenius is almost palindromic. And by this I mean that the coefficient g plus I can be recovered from the coefficient g minus I by multiplying it by the norm of P raised to the I. Since ag minus 1 is an integer, this tells us that the valuation of ag plus 1 is at least I. And in terms of the Newton polygon, this tells us that it will have to lie above the segment that I drew in blue that connects the point g, 0 with the point 2g, g. So yeah, the Newton polygon is some convex polygon that lives inside the triangle which has blue sides on the picture. And there's another piece of data that we can read from the Newton polygon that I introduced before. So I told you that I would use the notation u sub p for the number of roots of P sub p which have valuation 0. But by the fact that I was telling you on the previous slide about the Newton polygon, this should be exactly the x length of the segment which has slope 0. But that's precisely the length of such a segment. And another way to say this is that the length of the segment that the Newton polygon shares with the x-axis should be this quantity u sub p. Okay, so now I'm in good condition to tell you what it means for a prime of k to be ordinary for the abelian variety A. We say that prime p is ordinary if any of the four equivalent conditions that you see on the slide hold. The first condition is the one that one usually uses to define what it means to be ordinary. It is the assertion that the p torsion of the reduction of A modulo P over an algebraic closure has size P to the G. The second condition is the claim that UP has cardinality G. The third condition is the assertion that the central coefficient of the characteristic polynomial of Frobenius is not divisible by P. And the fourth characterization is the one that tells you that the Newton polygon coincides with the lower bound that we saw, that I explained to you that it has on the previous slide. And you can see that the last three conditions are equivalent among themselves, but what I've already told you on previous slides. So telling that UP of A, that UP of A is G, that the set of roots of the characteristic polynomial that have p evaluation 0 is G. It's forcing the Newton polygon to pass through the point G comma 0, and this forces the Newton polygon to coincide with its lower bound in a horizontal way, if you can make sense of what I mean by that. By saying that the central coefficient of the characteristic polynomial is not divisible by P, I'm also telling that the Newton polygon passes through the point G comma 0 in a vertical way, if you want. So the second and the third conditions are equivalent to the fourth one, and in fact these are the ones that you should keep in mind in this talk. Sometimes one calls this lower bound for the Newton polygon the Hodge polygon. And then in this talk, we will be concerned with the set of primes of K, which are ordinary for A. And more concretely, we'll be concerned with the conjecture that is often attributed to Serre that predicts that this set of primes, that the set of ordinary primes, has always a non-zero density for any abelian variety defined over a number field. And yeah, I guess the idea behind this conjecture is quite simple. The condition that P must divide the central coefficient of the characteristic polynomial of Frobenius is something exceptional. In general, it won't be divisible by P. So there should be many cases in which it's not divisible by P. But this becomes especially apparent when one considers the case of elliptic curves or of abelian surfaces. So let me explain why this is especially apparent in these cases. And for simplicity, let me take P a prime, which is of absolute residue degree 1, just for simplicity. Such primes have density 1 among the set of primes of K. So when one is concerned with density questions, it's harmless to restrict to them. And in fact, I will be doing this from now on. So yeah, in this case, if A is an elliptic curve, then the veil bound, the Hasse veil bound in this case, tells us that the central coefficient of the characteristic polynomial of Frobenius, which is just a trace of Frobenius in this case, has an absolute value which is bounded by twice the square root of P. And therefore, a prime can only fail to be ordinary if this A1 is 0, at least if P is large enough. So non-ordinary primes are really special. Something similar happens when A is an abelian surface. In that case, the Weil bounds tells us that the central coefficient of the characteristic polynomial of Frobenius has absolute value bounded by 6p. In fact, you can do the exercise if you've never done it. They tell us a little bit more. They tell us that the central coefficient is at least minus 2p, and it is strictly less than 6p. And therefore, a prime can only fail to be ordinary, or if a prime fails to be ordinary, then the central coefficient is limited to just 8 possible values. So something exceptional. Well, yeah, this stops being true as soon as the dimension is bigger than 3. We of course still expect that the set of ordinary primes has a positive dimension, a positive density, but it is no longer true that the possible values for which the central coefficient of the characteristic polynomial of Frobenius can attain if P fails to be ordinary. If this number of possibilities stays bounded as P grows, that's no longer true. Okay, yeah. Any questions so far?
I think we're good so far.
Okay. So now, yeah, I plan to tell you what is known. So here we see some dichotomy between dimension less than 2, dimension bigger than 2. And this dichotomy will manifest in what is known and what is not known. But before moving to this, let me put ordinary primes a little bit in context. Yeah, first I should say is that the quality of a prime being ordinary can be defined in much greater generality. And when you do so, I think that the right characterization that you should have in mind, the characterization that generalizes nicely, is the one asserting that the Newton polygon coincides with a Hodge polygon. And the second comment I want to make is that, yeah, that some sort of ordinary hypothesis is something that you encounter very common, that you encounter often in number theory. So just to give you two random examples, I don't have any pretension to give an exhaustive list here. 2 random examples is, so when one constructs p-adical functions, one certainly distinguishes between the ordinary case and the non-ordinary cases. Or for example, Hida theory is a theory for modular forms which are ordinary. But in these examples, so these are examples of local constructions. And yeah, you may argue that the abundance of primes is not really an essential part of the problem. But there are some cases when one really uses that there is abundance of ordinary primes. So one example of this is an automorphic lifting theorem by Boxer, Calagari, G, and Piloni, which takes as an input the abundance of ordinary primes for abelian surfaces, and that's the automorphic lifting theorem that leads to the meromorphicity of the Hasse-Weil function of a non-generic abelian surface defined over a totally real field. Here by non-generic, sorry, for a generic abelian surface. Here by generic I mean that the geometric endomorphism ring of the abelian surface is not Z. So by generic I mean that the endomorphism ring, geometric endomorphism ring of the abelian surface is Z. Okay, another example where one can use the abundance of ordinary primes is when one wishes to establish an average running time for an algorithm that that counts points modulo p for some curve defined over a number field up to some bound. So these algorithms, what typically do is to first compute the characteristic polynomial of Frobenius at P modulo P, and then leave these polynomials which has coefficients in Fp to a polynomial which has coefficients in Z, to the actual characteristic polynomial of Frobenius. And in this process of lifting the polynomial, you can use that the prime is ordinary. Good, so yeah, let's now move to what is known in dimension at most 2. And well, in these cases, not only the conjecture is known, it's not only known that there exists a set of ordinary primes with positive density, we know the exact density of the set of ordinary primes. And for an elliptic curve, this is due to Serre, and he shows that this density is either a 1 or 1/2, and it is 1/2 precisely when you're dealing with an elliptic curve which has potential complex multiplication, but not complex multiplication defined over the base field, and it is 1 otherwise. So we have a conclusive answer in dimension 1, and we have an equally conclusive answer in dimension 2, and this is due to Will Sawin. And Will Sawin shows us that the density of the set of ordinary primes for an abelian surface can only attain 3 values: 1, 1/2, or 1/4. And moreover, he tells us that this density is 1 if the abelian surface does not have any Q-bar isogeny factor with complex multiplication. And he distinguishes 2 more cases: the case in which A has complex multiplication by some quartic CM field. In this case, the density is essentially 1 over the degree of the reflex field attached to the quartic CM field. And then in the third case, that's the case in which our abelian surface is Q-bar isogynous to the product of 2 elliptic curves, one of which at least has complex multiplication. And then if I denote by F sub I, the endomorphism algebra of the factor, the elliptic factor E sub I, which is a field, then this density is essentially 1 over the degree of the compositum of F1 and F2. So let me explain to you what's the idea behind the proofs of these theorems. So I think time has come to give an aim to the aladic representation attached to A.
Sorry,
yeah.
Francesc, I can see Bjorn raised his hand. I can unmute him.
Yes, please.
Can you go back to the previous slide?
Yep.
So in this theorem of Sawin, so what about the case where A sub Q bar is the product of 2 CM elliptic curves? Do you consider that to be part of the second bullet, or?
I consider this part of the third bullet. So I should.
Oh, so 1 means at least 1.
1 means at least 1, yeah.
Oh, okay. Thank you.
So yeah, here I'm just copying Serre's theorem again, just for your convenience, and yeah, I just want to give a rough idea on how he proves the theorem. So yeah, row A was the aladic representation attached to A, so that encodes the action of the absolute Galois group of K on the aladic Tate module of A, and I denote by GL the Zariski closure of the image of rho sub A. And then Serre shows that the density of the set of primes, which are ordinary for the elliptic curve A, is 1 minus the proportion of connected components of this Zariski closure GL, on which the trace of the Aladic representation is equal to the function which is identically equal to 0. So that's the idea behind Serre's theorem. That's the idea. That's also the idea behind Sawin's theorem. So let me denote by high sub L the Aladic cyclotomic character. This codes the action of the absolute Galois group of K on the L power roots of unity in Q bar. And yeah, very beautifully, Will Sawin shows that the density of the set of primes which are ordinary for A is 1 minus the proportion of connected components of GL on which the trace of the alternating square of the Aladic representation conveniently divided by the Aladic cyclotomic character is equal to a function which is constant on that component. So yeah, you should compare this with what I explained some previous slides ago, by telling you that when a prime fails to be ordinary for an abelian surface, then the central coefficient is of the characteristic polynomial of Frobenius is limited to only 8 possible values. And in fact, in this case, one finds that constant means that that the function is equal to -2, -1, 0, 1, or 2. Okay, but I should say that so this completely solves the problem, yeah, in dimension at most 2. But I should say that the conjecture in terms of the existence of a set of primes of positive density was known before that, and that's due to some Aladic method that of Katz, Ogus and Serre. That it is actually the one that I will use for these results in dimensions 3 and 4. So let me recall this method for you. So now E will be a number field. It will be a field of coefficients. Let lambda be a prime of E that lies above the rational prime L that we've been considering. And S will denote some finite set of places of K. And we'll be looking at representations rho of dimension D, which are continuous and unramified outside this finite set S, and which take values in the completion of E at the prime lambda. So let me recall to basic notions for rho. I will say that rho is integral, or if I want to be more precise, OE integral, if for every prime outside S, the characteristic polynomial of Frobenius does not only have coefficients in the completion of E at lambda, but in fact it has coefficients in the number field E. And given some integer W, I will say that rho is of weight W if it is integral, and for every prime P outside this finite set S, every root of the characteristic polynomial of a Frobenius at P is a Weyl number of size the absolute norm of P raised to W. And recall that we say that an algebraic number alpha is a Q Weyl number, where Q is the power of some prime, if for every embedding of Q of alpha into C the complex absolute value of the image of alpha by this embedding into C is the square root of Q. Good. So now I can explain you the two parts of this elliptic method of Katz, Ogus, and Serre that's written in some paper by Ogus, but he attributes the first part to Katz, and then Katz says that this was explained to him by Serre. So let's call this the method of the three of them. And well, the first part tells you start with some representation, some continuous representation rho as the ones we've been discussing, which is integral of n of weight 1. Then there exists two things. First, a finite extension of k and a set of primes of this finite extension that I will call k prime, which has density 1, which is made only of primes of absolute residue degree 1, and with the important property that for any prime graphic P in this set R, its norm, which is some rational prime P, does not divide the trace of the image of Frobenius by the representation rho. The second part of the method, which I will call the proposition due to Ogus, starts with a very similar input. So rho is integral n of weight 1, but now we require that rho has dimension at least 3. We want to exclude dimension 2. And then the conclusion is also very similar. It's that there exists some finite extension k prime of k and some set of primes of k prime made of primes of absolute residue degree 1 and of density 1, such that for any prime graphic P in this set R, its norm does not divide the trace of the alternating of the image of the Frobenius element at P by the alternating square of the representation rho. So P does not divide the coefficient of T square in the characteristic polynomial of the Frobenius P. And yeah, my plan is to explain to you the proof, at least of the part due to Katz. But first, let's do what we all want to do, which is to derive the conjecture from these two propositions. So in the case of an elliptic curve and in the case of an abelian surface. In the case of an elliptic curve, what you do is to apply a Katz proposition to the elliptic representation attached to A. And well, this provides you some finite extension k prime of k on which the density of the base change of A to this extension of primes which are ordinary for this base change is 1. But then this immediately implies that there exists some set of primes in the base field which are ordinary for A and which has a positive density. And in the case of abelian surfaces, all you have to do is to apply Ogus' proposition to the elliptic representation attached to the abelian surface, which I know that has dimension at least 3. And now, yeah, let me check my phone because I want to know how am I doing with time.
So you're at 36 minutes, so you still have 15 minutes more or less.
Okay, sorry about that. I'm back. So yeah, but so yeah, that establishes the conjecture in dimension at most 2. What is known in higher dimension? So yeah, I should mention that there are partial results by Su when A is an abelian variety which has multiplication by some totally real field, which has degree equal to the dimension of the variety. In fact, in this work, Su also presents nice connections between this conjecture concerning the abundance of ordinary primes and the Saturday conjecture. Then, yeah, surprisingly, at least to me, the conjecture is also known when A is an abelian variety which has a trivial geometric endomorphism ring, and for which the Manford-Tate group is smaller than predicted by these endomorphisms. Like, for example, in the examples by Manford of dimension 4. And this is a result due to pink. And finally, another case where the conjecture is known is the case in which A has potential complex multiplication. And we will get back to this soon. But first, I promised you to prove the proposition due to Katz that I recall here for your convenience. So we have to find a finite extension K prime over K and a set of primes R in this finite extension K prime with 3 properties. So let me explain you how to find this finite extension K prime. That concerns some continuous representation rho, and therefore there's some lattice which is stable by the action of GK. So we can assume without loss of generality that the representation rho takes values not just in the completion of E at lambda, but in its ring of integers. And then let me take n, some natural number, sufficiently big so that the nth power of lambda does not divide the dimension d. And let rho bar denote the reduction of rho modulo this lambda to this n. And then I just take for K prime the field or the extension of K cut out by this reduction of rho modulo lambda to the n. That's going to be the K prime that we want. And then we define R as the subset of the set of primes of K prime, which have absolute residue degree 1, good reduction for A, which do not lie above the prime L, and which are sufficiently big. And then I claim that this is the set that will satisfy the crucial property 2 in Katz proposition. So the one that its norm P will not divide the trace of Frobenius. How does one show this? Well, let me call by AP this trace of Frobenius. And well, since the reduction of rho modulo lambda to the n is trivial, we have that this AP must be congruent to the trace of the identity modulo lambda to the n. But the trace of the identity is d. And we chose this so that it's not congruent to 0 modulo lambda to the n. So this in particular is telling us that this AP is not congruent to 0. So if it's not congruent to 0, and I suppose that condition 2 in the proposition fails, there will exist some non-zero integer Vp such that AP is P times this non-zero integer Vp. But then, yeah, you compute the norm of Bp, it is the quotient of the norm of AP by the norm of P, and because rho is a representation, an integral representation of weight 1, you easily see that as soon as P is big enough, bigger than d squared, then this norm will be less than 1, and therefore Bp will be 0, which is a contradiction. So that's the proof of the proposition by Katz. Any questions? So let's go back to the previous slide. In the previous slide, we derived some abundance of ordinary primes by applying the propositions of Katz and Ogus to elliptic representations attached to abelian varieties. But when our abelian varieties have extra multiplications, then they are endowed with another type of representations, the so-called lambda-adic representations. So our idea will be to apply the propositions of Katz and Ogus to these other representations, to these lambda-adic representations. And since I promised that this talk would be friendly to graduate students, to young people, let me recall you what a lambda-adic representation attached to an abelian variety is. So suppose that our abelian variety is such that its endomorphism algebra contains this number field E that we've been considering before. Then, so this E acts on A, and by functoriality, this action gives rise to an action of E on the elliptic Tate module of A. And yeah, I will use this to define some space V lambda in the following way. So I take the tensor product of the elliptic Tate module of A, VL, with the completion of E at lambda over E tensor QL. And maybe I should precise which QL algebra map I'm considering here to take this tensor product. Which QL algebra map from E tensor QL to E lambda. Well, the one I'm using is, so E tensor QL is isomorphic to the product of the completions of E at the primes of E which lie above L, and then I compose this isomorphism with the projection to the lambda component. And then one sees that this V lambda is a vector space over the completion of E at lambda, which has dimension 2G divided by the degree of E over Q. And now, in fact, I can endow these spaces V lambda with an action of the absolute Galois group of K by letting it act naturally on VL and trivially on E lambda. And this gives rise to the elliptic representation attached to A, which I will denote by rho sub lambda. And yeah, these representations are integral, have weight 1, and one has a GK equivariant isomorphism between VL and the direct sum of the spaces V lambda, where lambda rhymes over the primes of E that divide L. You can find all this very well explained in Ken Ribat's thesis. So yeah, from now on, S will be a finite set of primes of K that contain the primes of pad reduction for A. And for any prime P, which is outside SL, and SL is just the union of S and the set of primes of K which lie above the prime L, I will set a notation, analogous to the notation I use for the characteristic polynomial of Frobenius acting on the elliptic Tate module. I will denote by P sub P of V lambda the characteristic polynomial of the image of Frobenius by the representation rho lambda. And then the GK equivariant isomorphism between VL and the sum of V lambdas translates into the fact that the characteristic polynomial of Frobenius factors as this product of the polynomials P sub P of V lambda. So how do lambda-adic representations connect to the problem that concerns us about the abundance of ordinary primes? Well, the mere existence of these representations as OE integral, or in fact as irrational, implies the conjecture for abelian varieties which have potential complex multiplication. And I will explain you why. So what does it mean that A has a potential complex multiplication? It just means that there exists some number field of degree twice the dimension that injects into the geometric endomorphism algebra of A. And yeah, as we have argued already before, without loss of generality, we may in fact assume that A has complex multiplication, and by this I mean that we have an injection of this number field E in the endomorphism algebra of A. And then I claim that any prime of absolute gradual degree 1, which is totally split in this field E of the complex multiplication, is ordinary. How does one prove this? Well, one has to choose well the prime L that will lead us to consider the spaces V lambda. And by choosing well this prime, I mean choosing it totally split in E. And why that's the good choice? Well, I told you that these V lambdas have dimension 2G divided by the degree of E as a vector space over E lambda. So they have dimension 1 over E lambda. If I choose L totally split in E, they will have dimension 1 over QL. And then it follows from that the composition of the lambda in terms of the of VL in terms of the sum of these spaces V lambdas, that the roots of the characteristic polynomial of Frobenius are precisely the images of Frobenius by the lambda-adic representation rho lambda. And then, yeah, Weyl's theorem, as I already used on the first slide of the talk, tells us that the roots of the polynomial P sub P come in pairs, which multiply up to the norm of P. But now the fact that these roots are irrational means that their valuation will be integral, and since the sum of the valuation of a pair of complex conjugate roots must be 1, this means that the set of valuations of such a pair must be 0, 1, 1. So each pair provides a root which is a p-adic unit, and we get G p-adic unit, G roots which are p-adic units in total, and therefore P is ordinary for A. Yeah, I'm a little bit short on time. Well, but let me tell you what one gets when one combines the existence of these representations V lambda with the propositions of Ogus and Katz. So at least what I could prove is that if A is an abelian threefold whose geometric endomorphism algebra contains an imaginary quadratic field, then one can deduce the abundance of ordinary primes. And yeah, by Albert's classification, this leaves us with only 2 types of abelian threefolds for which we don't know the abundance of ordinary prime, the generic abelian threefolds, and the abelian threefolds which have multiplication by some totally real cubic field. And in that case, that's theorem 2, I could not have derived the abundance of ordinary primes, but I could derive it under some assumption. And this assumption is that, well, there's some finite extension F of the ground field over which the abelian variety attains real multiplication. Let's assume that this field does not contain the field of the real multiplication. In that case, you can derive the abundance of ordinary primes. Just to give you 2 examples where these theorems apply, The first one applies to the case of Picard curves. These are curves given by an equation y cubed equals to some separable degree for polynomial, and the imaginary multiplication in this case is obvious. Q03 acts on the Jacobians of such curves. An example where theorem 2 applies is the case of the abelian varieties attached by Eichler and Shimura to classical new forms of wave 2 and cubic coefficient field. And I think I'm already running over time, right?
Yes, you can conclude whenever you want.
So yeah, that's what I could prove in dimension 3, and then I did some incursion in dimension 4. So that's the analog of theorem 1 in dimension 4, but I had to make some additional assumption in this case. So I'm assuming that the geometric endomorphism algebra of A contains some quadratic imaginary field E, but I'm also assuming that the signature of the pair E and A is 2, 2. And you can derive the abundance of ordinary primes. I should tell you maybe what I mean by the signature. So the signature is some integer tuple indexed by the embeddings of the field E into C, and yeah, essentially the tau component of the tuple is the multiplicity of the action of E on the complex cotangent space via tau. And yeah, here I had some remark. Well, of course, the theorem applies when geometric endomorphism algebra is exactly an imaginary quadratic field, but it also applies when it contains it strictly. And an interesting case when it contains it strictly is the case in which this geometric endomorphism algebra is a quaternion algebra, because quaternion algebras always contain imaginary quadratic fields. So this theorem also applies to abelian fourfolds of Albert type 2 or 3, which are sometimes called fake abelian surfaces. And I had planned to explain you the proof of theorem 1, how one combines the existence of these lambda-adic representations with the propositions of Ogus and Katz, but I'm over time, so yeah, I won't do that. There is some mild generalization of these methods to higher dimension for some abelian varieties, which essentially look like the ones that I consider. And yeah, I will finish by thanking the organizers again, and by telling you that the way that Victoria convinced me to give this talk was by telling me that it would be a revival of some great winter school we had in Lumini back in 2014. So let me finish by sharing with you some picture that shows the extraordinary slopes of the Calangs in Lumini. So thank you for your attention.
Thank you very much, Francesc, for this wonderful talk and for this wonderful picture that make us imagine ourselves in Siam, in Lumini. Are there any questions for Francesc? So I see 2 hands raised. So Berinde, can you kindly unmute yourself? Sejong, can you kindly do so, please?
Sorry. So you are co-host.
Two questions.
Oh,
yes, but
yeah, sure. I can allow me.
Thank you. So Piotr Krasen has a question.
Hello, can you hear me?
Yes,
Yep.
definitely.
Yeah. So Francesc, thanks for the clear exposition of your talk. I had a question about: do you expect there to be only finitely many values of the density, like we saw in dimensions 1 and 2?
Yeah, that's a good question. I would expect a finite number, yes. It even looks like it's 1 over some power of 2, right?
But
so
it's
far. Yeah, but I don't know. I don't know if anyone has conjecture what these possible values of the density can be.
Okay, thanks.
Okay. Thank you for your question. So Piotr Krasen, you have a question as well?
my question was similar to that, because if you take a product of elliptic curves, you basically see that you have dyadic expansion, right? Depending on what product you took. But can you get irrational number for the density? Because if you go with the product to infinity, say, make it large, your dyadic expansion will grow. So I don't know, you expect only rational numbers for densities or maybe irrational? That's my first question. And the second question is, I wonder why in Sawin's theorem you have this twist by inverse of cyclotomic character. And in Serre's theorem you didn't have.
Yeah.
So maybe it's naive question, but
No. Yeah, so the first question is, I don't know. I would expect rational numbers, but I don't. Well, yeah, in fact, that. So yeah, a more precise version of the conjecture is that after some finite extension of the base field, the set of ordinary primes should have density 1.
Oh.
So yeah, it looks very much like this does not imply that on the base field it would have to be a rational number, but it kind of suggests it, I would say. The second question, so that's related to what I was explaining when motivating the conjecture. So for an abelian surface, you're looking at the coefficient of t squared. So it's something of weight 2. So it's it can be divisible by p without being 0, and dividing by the cyclotomic character has the effect of normalizing. So rely on the interval from -6 to 6, from -2 to 6.
Oh, I see. Okay, thank you.
Perfect. Are there any questions so far? Okay, I suggest that we thanks again Francesc Fité for this wonderful talk.